Hi everyone. Today starts our first day of Logarithms, section 5.3, our Intro to Logarithms notes. And to actually start off our learning, we're going to watch a quick TED Talks that will help us to understand why logarithms were so important and where they came from.
As you can imagine, 400 years ago, navigating the open ocean was difficult. The winds and currents pushed and pulled ships off course, and so sailors based their directions on the port they left, attempting to maintain an accurate record of the ship's direction and the distance sailed. This process was known as dead reckoning, because being just half a degree off could result in sailing right past the island that lay several miles just over the horizon. This was an easy mistake to make. Thankfully, three inventions made modern navigation possible: sextants, clocks, and the mathematics necessary to perform the required calculations quickly and easily. All are important. Without the right tools, many sailors would be reluctant to sail too far from the sight of land. John Bird, an instrument maker in London, made the first device that could measure the angle between the sun and the horizon during the day, called a sextant. Knowing this angle was important because it could be compared to the angle back in England at the exact same time. Comparing these two angles was necessary to determine the longitude of the ship. Clocks came next. In 1761, John Harrison, an English clockmaker and carpenter, built a clock that could keep accurate time at sea. A timepiece that could maintain accurate time while on a pitching, yawing deck in harsh conditions was necessary in order to know the time back in England. There was one catch, though. Since such a timepiece was handmade, it was very expensive, so an alternate method using lunar measurements and intense calculations was often used to cut costs. The calculations to determine a ship's location for each measurement could take hours. But sextants and clocks weren't useful unless sailors could use these tools to determine their position. Fortunately, in the 1600s, an amateur mathematician had invented the missing piece. John Napier toiled for more than 20 years in his castle in Scotland to develop logarithms, the calculation device. Napier's ideas on logarithms involved a form of 1 over e and the constant 10 to the 7th power. Algebra in the early 1600s was not fully developed, and Napier's logarithm of 1 did not equal 0. This made the calculations much less convenient than logarithms with a base of 10. Henry Briggs, a famous mathematician at Gresham College in London, read Napier's work in 1614, and the following year made the long journey to Edinburgh to meet Napier. Briggs showed up unannounced at Napier's castle door and suggested that John switch the base and form of his logarithms into something much simpler. They both agreed that a base of 10 with the log of 1 equal to 0 would greatly simplify everyday calculations. Today we remember these as Briggs' common logarithms. Until the development of electric calculating machines in the 20th century, any calculations involving multiplication, division, powers, and extraction of roots with large and small numbers were done using logarithms. The history of logarithms isn't just a lesson in math. There were many players responsible for successful navigation: instrument makers, astronomers, mathematicians, and of course sailors. Creativity isn't only about going deep into one's field of work. It's about cross-pollination between disciplines too.
So now that we have an idea or an understanding of the connection between logarithms and history, let's now actually understand what logarithms are and how we are going to start using them. So to do that, let's get into our notes for today. If you haven't gotten a highlighter out yet, that would be fantastic. And as we're taking these notes, keep that video in mind, You are studying some of the math that was done by literally the brightest and smartest mathematicians of their time. So even who was considered an amateur mathematician back in the 16th and 17th century created mathematics that was key to navigation. So now let us put on our learning caps and join those brilliant mathematicians in understanding what logarithms are all about. I am recording this at school, so if you hear a bell, that is not our bell. And if you're at home taking these notes, then obviously it doesn't apply to you. But if the bell rings, don't let it throw you off. So our general form, and again I'm going to be highlighting as we go, f of x equals a times log base b. So when I say the word base, immediately that means I'll be writing small and low. Just like an exponent, when we say raised to a power is up high, base means a subscript. So this b is much smaller and lower. Log base b of x minus h plus k. Please highlight that. I'm putting it in a box instead of highlighting so that if I were to print these out for someone, it prints out correctly. But whatever you see me put in a box like this, I intend for you to highlight with your highlighter. Formally, let's look at the definition of the general model we just wrote. Let b and y be positive numbers where b is not equal to 1 the logarithm of y with base b is denoted by log base b of y, log base b of y, and is defined as follows. And again, please highlight this. Log base b of y equals x. This is going to be one of the most important things we write down today. Log base b of y equals x. This has a connection to exponents. So I want to show you first how I'm about to do this. Off to the side, let's rewrite. Log base b of y equals x. Circle the base. So the base is b, circle it. Draw an arrow in the direction of the equal sign and loop it around. And what we're doing here is we're actually guiding how we're going to read this. Because this can be read b to the x equals y. b to the x equals y. What this means is logarithms are the inverse of an exponential function. So as of today, we now have a new tool in our toolbox, which is logarithms, the inverse of exponents. Think back to the real world questions we had worked on where I had asked questions like, in what year will the profit be $80,000? And we had to use the tables in the graphing calculator to figure that out because we had no way of solving for this guy. Starting today, we're going to learn how to make that happen because if you look at this here. Log base b of y equals x, where x is that exponent. So exponential equations and logarithmic equations are inverses of each other. Remember, today is just the intro day, so we're getting familiar with the language, and we're about to get familiar with properties. All of these properties, as we move forward, would make some great flashcards. First, though, let's practice a little bit. So the directions say, rewrite the expression in exponential notation. So number 1 is log base 5 of 1 equals 0. So I'm looking to go from logarithmic notation to exponential notation. To do that, we will circle the base, draw our arrow in the direction of the equal sign. So if my equal sign was over here, I would have gone this way. This reads 5 to the 0 power, right? Look at the connection. What the logarithm equals is the exponent. So 5 to the 0 power equals 1. And that's true. 5 to the 0 equals 1. Anything to the 0 power equals 1. Try this one on your own. Log base 5 of 1/5. So we could use parentheses or not, like this 1 could have been in parentheses. It's a nice way of keeping the argument together. Log base 5 of 1/5 equals -1. Please rewrite that in exponential notation. Let me join you. I'm going to circle the base, draw an arrow in the direction of the equal sign, and come around. This reads 5 to the -1 equals 1/5, which is also a true statement. So we just went from logarithmic notation to exponential. Now we're going to go the other way. Now I'm going to give you exponential and we're going to write them as logs. So the directions here say rewrite in logarithmic notation. Number 3 is going to be 3 to the 4th equals 81. One strategy is to write the general form off to the side. So our general form was log base b of y equals x. Circle the base, come around, and that becomes b to the x equals y. So now we're looking to go from this to this, from exponential to logarithmic notation. So just take a second and see if we can have a thought about what piece goes where. If I were to visualize, here's my base, here's my exponent, here's the result. Out loud, say to yourself, log base b. But I don't have a variable, I have a number. My base is 3. So it's going to be log base 3 of what? Of the result, of the answer. So log base 3 of 81 equals the exponent, which is 4. So 3 is the base, 81 is the answer, 4 is the exponent. We're equaling the exponent, right? We're undoing an exponential notation. And we can always double check. If I circle the base and I come around, do I get what I started with? 3 to the 4th equals 81. 3 to the 4th equals 81. I am in good shape. Try number 4 on your own. 7 to the x minus 4 equals 3. And if you're not sure, rewind and re-listen to the conversation that allowed us to do number 3 before you try doing number 4. To do this, I'm going to remind myself about what pieces I have over here. 7 is my base. X minus 4 is the exponent. 3 is the answer. So log base, my base is 7. So log base 7 of the answer, which is 3, equals the exponent x minus 4. Let's double check if we did this right. I should be able to circle the 7 and come around and see if we match. 7 to the x minus 4 equals 3. I'm in good shape. This is super powerful because as of yesterday, or as of our last class, if I had given you this, we had no way of finding out x. But notice, as soon as we switched or rewrote this with logarithmic notation, x is no longer stuck in the exponent, and it's something that I would actually be able to solve for. Very cool. Let's now talk about some special logarithm values. These are what I was mentioning would make some great flashcards. Let's first talk about the logarithm of 1. Log base b of 1 equals 0, and that is always true. So on one side of my flashcard I would put log base b of 1, and on the other side I put 0. Let's understand why. Think about what would happen if I rewrote this. So I've got log base b of 1 equals 0. I circle the base, come around. That would become b. Let me see if I can fit this side by side. Let me move this over. B to the 0. So if I rewrite this, b to the 0 equals 1, anything to the 0 power will always equal 1. So log base anything, log base 100, log base 5, log base 6 of 1 will always be 0 every single time. Now let's talk about logarithm of base b. So what we're saying is the base and the argument are the same. Logarithm base b of b. That's what this is saying. That will always equal 1 every single time. So you're saying you're taking the logarithm of the base. Because is important. We want to understand why. Let's say I had log base b of b. If I circle the base and I come around, that would be b to the first equals b, which is true. So for this to be a true statement, this always has to equal 1, because b to the first power will equal itself. Let's look at some examples. Let's look at log base 3 of 1. What does that equal? Well, based on our property, log base anything of 1 will always equal 0. And off to the side, we'll make note of our because. 3 to the 0 power equals 1. Second example, log base 7 of 7. What does that equal? Well, when the base and the answer are the same, the exponent has to be 1. Because 7 to the first power equals itself. Let's do some practice. The directions say evaluate the following: logarithmic expressions. Number 5 is log base 3 of 81. We're being asked to evaluate, so we should result in a numerical answer. Let's rewrite. How am I going to do this? Well, it doesn't say equals a number, but we are trying to actually find what this equals. And now how can I rewrite this so that my brain sees this as an exponent instead of a logarithm? Circle the base, arrow in the direction of the equal sign. What we're really saying here is 3 to what power equals 81. Because remember, log base b of the answer equals the exponent. So I don't know the exponent. I know the base and I know the answer. I don't know the exponent. 3 to the x equals 81. So 3 to what power equals 81? The answer is 4. And that we should know from our just general exponent knowledge. 3 to the 4th equals 81, so my answer is 4. Number 6, log base 9 of 3 is what? Once again, we don't have a result yet, so let's just say equals x because that's what we're trying to figure out. We're looking for the exponent that makes the following statement true. 9 to what power equals 3? In other words, 9 to the x equals 3. What are we thinking? 9 to what power equals 3? I'm hoping we're thinking square root or fractional exponents. The answer is 1/2. Remember, 9 to the 1/2 equals 3 is the same as saying square root of 9 equals 3. Last but not least, log base 1/2 of 8. So if you want, press pause and give this one a shot for a little bit before I go into it. Once again, I'm going to set this equal to a number that I don't know yet, but I'm about to figure out, because what I now realize I'm really asking myself is 1/2 to what power equals 8? Remembering our negative exponent knowledge will help me to remember that it needs to be -3. So I'm going to add another remember note here. Negative exponents is how we would get that fraction to flip. 1/2 to the -3. If I send in that power, it becomes 1 to the -3 divided by 2 to the -3. Negative exponents move, so this would become 2 to the 3rd divided by 1 to the 3rd, which is 8. You could also think 2 to what power equals 8. Then make that number negative. So for example, I'm considering 1/2. I know that 2 to the 3rd equals 8. So 2, that's not what I meant to say. 2 to what power equals 8? Trying to think of how to write that. I'm just going to leave it as 2 to what power equals 8, because I know that that's a 3, and then I have to decide what connection does it have to 1/2. I don't want to overtalk this example, so I'm going to leave it at that for number 7. But we'll continue to look at examples like this in our practice tomorrow. We have 2 special types of logarithms to talk about. The first one is called the common logarithm. that in a highlighted box or highlight it. It's a key vocab word we're about to discuss. A common logarithm is any logarithm with base 10. So when we write log base 10 of x, that is literally the same as log of x. So on your calculator, if you find the log button on your calculator is log base 10. It is set to be that automatically. So just like if you think about when somebody writes x, that's technically 1 as a coefficient, we just never write it. And also x to the first, like these ones never get written, but they technically are there. If you ever see log of x, that really is log base 10 of x. We just don't write it because it's understood that it's there. We should highlight that too, because that's really important. And in words, it's denoted simply by log no written base. So it technically looks like we don't have a base, but again, log of x, we have that invisible log base 10. The second type of special logarithm is natural logarithm. And I'm hoping that word natural is bringing a certain letter to mind that we just talked about. Natural logarithms is a logarithm with base e. And in terms of our standard notation here, log base e of x, we never actually write that, ever. It's denoted ln of e. We don't say ln, we say natural log of e. That's what that ln stands for. And again, you can find the natural log button on your calculator. It says ln, but we never say ln. We say natural log of e. We also have an important definition that the natural log of e will always equal 1. Because you're saying log base e of e, right? We can technically, log base e is the same as saying natural log. Well, log base e of e would have to equal 1 for our little rewrite to be true. E to the first equals e. The connection up here would be log base 10 of 10 has to equal 1 because 10 to the first power equals 10. So same idea. Just like log base 10 of 10 would be 1, natural log of e has to equal 1. And again, just to have our notation represented in words, just in case that's helpful for us, denoted by log base e, or simply ln. And where does ln come from? ln is written. Comes from natural log written backwards. See? Watch. L N. And it's written backwards because of the Latin language. So ln actually stands for natural log, but it's written L first because of language rules of Latin origin. Just to reiterate, we will never say, you'll never hear me say ln of 8. We never say that. Natural log of 8 will be our language. The last piece of our intro knowledge today is how to use our calculator, evaluating common and natural logs on the calculator. To do that, we will need the change of base formula. Change of base formula. Change of base formula says, if the log is not base 10. So remember, the calculator can do log base 10 only using that log button. So if the log is not base 10, we need to use this formula. Which is just called change of base. We need to use change of base to evaluate on the calculator. Our change of base formula will be log base c of u. I chose 2 random variables to stand for numbers. Log base c of u will equal log base b of u divided by log base b of c, where b equals 10. That's the key, is that this formula changes it to log base 10. Let's look at some examples. Log base 3 of 7. The way that I remember this the best is look at like the top shelf first. So this is going to be log of 7 divided by log of 3. I can type that right into my calculator. So grab your calculator, press pause if you need to go get it. Log of 7, close the parenthesis, divided by log of 3, close the parenthesis, and we should be getting 1.771. Our last example is going to be log base 5 of 32 thirds. I choose to use parentheses here just to make sure it stays nice and neat. Again, kind of think top shelf first. It's going to be log of 32 thirds divided by log of 5. Press pause and use your calculator. Make sure you close that parenthesis to make sure the argument is all set. So what I mean by that is log of 32 thirds, close the parenthesis before you hit the divide button. Log of 5, and we get 1.471. That ends our first day of our intro to logs, and we will be practicing all of these properties in class. Great job, guys.